Hello and good afternoon, everybody. Thanks so much for coming to this month's Tech Mashup. I'm Kelly Fornell. I'm the CEO of Tech Manitoba. Thanks for spending your lunch hour with us. Just as I like to start every Tech Mashup, can you give me a virtual thumbs up to let me know if you can hear and see me just fine? I'm seeing the little purple circles at the right of the screen. So thank you so much, everybody, for acknowledging that all's good to go. So the other way we like to start events, of course, is with a formal land acknowledgement. So again, welcome to today's Tech Mashup. The topic here is quantum computing, the next frontier of digital transformation. And before we switch over to that topic and our amazing speaker, I wish to acknowledge that we are on Treaty 1 territory, the traditional lands of the Anishinaabe, Cree, Oji-Cree, Dakota, Dene peoples, and the homeland of the Red River Métis Nation. I recognize that our community and our work in the tech sector benefit from these lands and the resources that are here. At Tech Manitoba, we are committed to fostering respectful and inclusive spaces within the tech community. We recognize the importance of Indigenous knowledge, creativity, and contributions in shaping innovation. And as we work to advance tech and digital growth, we remain dedicated to building relationships and partnerships that respect Indigenous sovereignty, knowledge sharing, and collaboration. We are grateful to live, learn, and work on these lands, and we are committed to working towards a future that respects the histories and the ongoing contributions of Indigenous peoples in Manitoba and across Canada. So some of our upcoming events that we have that we very much hope that you'll be interested in and might attend. The first one is later this week on Thursday. It is the 5th anniversary birthday bash for the Manitoba Women in Tech group. It's going to be held at the SKIP headquarters. It's from 5 to 7 p.m. For information on registration for any of the events, including the 5th birthday bash, you can head to our events page on our webpage, and registration information is located there. A next upcoming event that we have is Plugged In. It's using AI to grow on LinkedIn. It's Monday, December 1st from 5 to 8 p.m. at Red River College Polytech at the Exchange campus. And then, of course, I'm sure you've heard us talk about, and it's only going to increase because we're always excited. It's MB Tech Week. It's coming up February 22nd to the 28th. We have our last call for sponsorship. The deadline is the November 30th, so it's just coming up. If you've got any thoughts about how you might want visibility for your company, reach out to myself or Shaylin, and we'd be happy to talk to you about any existing sponsorship opportunities. We have our event hosting proposal deadline due December the 31st. So if you've been thinking, how might I'd like to, host an event, or I think my organization should. Absolutely, we want to be able to feature your event on the calendar. We have lots of suggestions if you're unsure of which type of event might resonate well with our community. So save that week, check out the calendar. We've got some events that are popping up, and certainly lots more to come the new year. So those are the 3 events that I very much hope that you'll be able to attend and help spread the word about. Okay, so now the main event, which you've all come for. It is my pleasure to introduce today's speaker, Curtis Nybo. He is the Director of AI and Quantum Computing at CGI. Curtis leads CGI's global research and development efforts in some of the most transformative technologies shaping our world today, including artificial intelligence, agentic frameworks, machine learning, and quantum computing that he'll speak about later on this session. He heads CGI's quantum computing practice. It is an international team dedicated to building and deploying real-world quantum applications. Under his leadership, the team is pushing the boundaries of what's possible through advanced computation and applied innovation. Curtis brings more than a decade of experience across both industry and academia, where he has built a reputation for translating complex theory into practical, impactful solutions. His background blends the precision of applied mathematics and physics with a deep commitment to accelerating the advancement of next-generation AI systems. And here's the part that I really think is even more interesting. Curtis holds a master's degree in quantitative finance, and he is currently pursuing a second master's in astrophysics, further proof that becoming an expert in one frontier technology simply wasn't ambitious enough. So please join me in welcoming Curtis onto the virtual stage.
Thanks, everybody. That was a lot. I'm not that great, but I appreciate the intro. So thanks for having me today to talk about quantum computing. That is something that I do spend a lot of time doing. And yeah, so my name is Curtis Nybo, as I said, and I'm a director of AI and quantum computing at CGI. For those who haven't ever heard of CGI, or maybe you're not very familiar, we're one of the largest IT services integration companies. So we're up there with Deloitte, Accenture, IBM, those type of companies. So we're a very large tech company. We have a presence in 40 countries and a total of around, I think, 100,000 employees that work directly in the tech sector. In Western Canada, where I'm located, we have, I think, 12,000 employees. I could be wrong. Maybe that's all of Canada. And we are spread across Manitoba, Saskatchewan, Alberta, BC, and we spend a lot of time working through different industries, from public sector to private to oil and gas to manufacturing, you name it. We've worked in it. And so where I spend most of my time is on the emerging technology side. So I work on the latest and greatest. I like to say that we have the best of both worlds, where we can take the latest advancements in research and apply it to clients and to business, to find where we can actually use this new technology and the new advances to actually solve business problems. So I do a lot of hands-on development in the AI space and the quantum computing space. And as was in the intro, our quantum computing practice is led out of Western Canada, but it is a global effort overall. We have about 60 members in total, where about 20 to 30 of those have advanced degrees when it comes to physics or computational physics or quantum computing directly. And we spend a lot of time doing the same thing. So trying to take the latest and greatest advancements from research and find ways to apply it, which is a little bit trickier in quantum computing, as you'll find out, compared to AI, but it's a pretty interesting area. And so we have teams in Europe, the UK, the US, a lot in Canada. And as you'll find out throughout the slides, we work with a lot of the biggest quantum computing providers. So hopefully everyone can hear me okay, and you can see my screen. I'm going to walk through a few slides. I think I have until about an hour from now, 40 minutes, 50 minutes from now. So I'll probably try and get through a lot of the content, and then I think we do have some dedicated time at the end for questions. But I think you can pop your questions into the chat as we go along, and we'll tackle them at the end. So that's a long-winded intro for myself and CGI, but let's get into our quantum computing primer. So this is the presentation we usually present to clients or industry around what quantum computing is. So it's a good baseline to understand what quantum computing is, how it works, what are the use cases, what does the landscape currently look like. There's a lot of things happening in the news. How do we approach it from CGI's perspective? I won't spend too much time on that. And then we'll talk about how you can get started with quantum today. How real is it? How do you actually start with the development and putting some things into practice around quantum computing? So that's where I will leave off, where you can kind of take it away and work on it at home. So we'll start out with a bit of a quantum computing primer. What is quantum computing? How does it work? And so we'll start with just a little bit of background around quantum computing as a whole. So traditional computing, as it's transformed our world in the last few years, especially with AI, it's fundamentally built on classical Newtonian physics. And so as we advanced in the classical computing, scientists realized that it starts to fall short when we're modeling really complex microscopic systems, things like chemical reactions, molecules, material sciences. And that's because these systems, they behave according to the rules of quantum mechanics and not the classical Newtonian physics. It starts to break down when you get into the very, very small level of reality, really. And so quantum computing was developed to address this limitation. It allows us to simulate and analyze natural phenomena that classical computers struggle with. So these systems were originally built to simulate quantum systems directly, rather than just kind of estimate them. So if you wanted to estimate the trajectory of a thrown baseball, for example, you could calculate the weight of the ball, the velocity of the throw. You could take into account the wind, all kinds of different factors. But you would still just be estimating its trajectory with all kinds of different assumptions, where alternatively, you could just throw the ball and you would get the actual result. And so that's what they ended up doing with quantum computers. They built these to initially simulate these quantum systems directly so that they didn't have to just try and estimate them using different technology. And then they realized really quickly that we can actually use these computations. And so this was done back in the 60s to 80s with Feynman and a lot of famous physicists that initially kind of found out how this can work. And so there's two key differences between classical and quantum computing. Classical computers use bits, so these are the binary digits we're all used to. But a bit can either be in a state of 0 or 1. Everything in your computer is ultimately reduced to combinations of these binary states, whereas quantum computers, on the other hand, they use qubits. And so instead of using these physical switches like a regular bit does in your laptop or smartphone, these qubits leverage particles at the atomic level. So things like ions or photons, and that represents the information that a regular bit would represent. And so these particles are placed into delicate environments like the one shown on the right side of the screen here, which is an actual D-wave quantum computer. And you'll notice that it's super cooled to temperatures colder than outer space, which is necessary to keep those quantum states, those qubits, stable. And so what's so special about qubits? Well, they gain their power from two very unique phenomena, superposition and entanglement. And so we'll talk about how this makes quantum computers really tick and gives them their advantage. And we'll start with superposition. You might have heard a lot about quantum computers when it comes to superposition and entanglement. But what that really means is that with superposition, for example, a classical bit, relating it back to what we all know, can be either a 0 or a 1. It's deterministic. Whereas a qubit, thanks to superposition, can be in 0 or 1 or any range in between at the same time. It can be in a probability of a 0 or 1 state. It's not going to be in one or the other all the time. It can be in both basically at the same time. So if you think of a spinning coin, it's kind of showing that both heads and it's in the state of heads and tails until it lands. So when it's spinning, it's not just in heads or tails, it's in a superposition of both of those states, for example. And so it's only when you look at the coin or measure it that it becomes either heads or tails. And so superposition isn't about just being in two states at once. It's about being in all possible combinations of those states. So you could be in 70% in state 0 and 30% in state 1, or any combination of that. And once it's measured, it collapses to one of those single states. And so measurement is important when it comes to these quantum systems. So it affects everything directly. When we think of measurement in our day-to-day lives, we don't really even take it into account. So if you measure the speed of a baseball, for example, the photons bouncing off the baseball from the radar gun, they don't affect its speed. The effect is negligible. However, at the quantum level, when we actually measure something, it really does affect the outcome. And so when we're measuring, say, the spin of an electron, so whether it's spin up or spin down, the magnetic fields used to detect that spin will affect the electrons themselves. Or that same photon could be intercepted by polarized filters, which I'll actually give an example to kind of help visualize how superposition works. But the main thing about superposition is it allows quantum computers to process a vast number of possibilities simultaneously. So it makes them highly effective for optimization and those simulation problems. And the second thing is entanglement. So when two qubits are entangled, their state becomes linked no matter how far apart they are. And this is a very bizarre thing to wrap your head around. Even Einstein called it spooky action at a distance because it just is kind of pretty counterintuitive. And the way entanglement works is when these two qubits, their states are linked together. If you imagine those two coins, for example, so you have two coins, one in New York and the other in Tokyo. If both coins are tossed and they're entangled, you'd expect each to land on heads or tails randomly. However, because the coins are entangled, one is going to land on one randomly and the state of the other one is instantly going to be decided. So if the coins are entangled and one in New York lands on heads, then the other one in Tokyo will instantly land on tails. It'll land on the other option. And so this is no matter how far apart they are. And so the outcome of one coin directly determines the outcome of the other. So even without any physical connection between them. And so that's kind of the strange instantaneous connection of quantum entanglement. But there is a caveat to this. You can't use this to transmit information faster than light. You might have seen the show The Three Body Problem, and that's not really possible for the way they represent it. If you measure the state in one particle, it just reveals the state of the other. This information, it can't be used to send messages or signals because you only can know the outcome. You can't control or influence what that outcome will be. And so it doesn't violate principles of relativity or allowing faster than light interaction. But this matters because this allows for incredibly fast state sharing between qubits. And it's vital for solving problems with kind of a deeply interconnected structure. So things like modeling molecules or solving complex logistical problems. And so that's things like protein folding. Classical computers might take years or even centuries to run those calculations, whereas a quantum computer can simulate those much more efficiently and much more directly. So kind of to sum it up, quantum computing is based on quantum physics, and it uses qubits rather than just bits. And unlike classical bits, those qubits exist in multiple states at once in a state of superposition, and they can influence one another over large distances, which is entanglement. And so again, it just allows for much faster and more efficient computation. And a way to think about it is it's a completely new way of computing. It's not like AI where we're using existing classical approaches, and this is just kind of an add-on to it. This is a complete fundamental new way of actually using a computer or having a computer do something. So just to kind of understand how superposition works, because it's kind of strange, you can actually experiment with this, and you can see this directly if you have two pairs of sunglasses and even your cell phone to be able to see how light waves interact. And so this is using polarized light. So if your sunglasses are polarized, your phone has a polarized filter. And what this means is that light waves can vibrate in different directions. So a horizontal polarizing filter only lets light through that vibrates horizontally. A vertical polarizing filter only lets light through that's vibrating vertically. So if you put a horizontal filter and follow it immediately with a vertical filter, you'd expect nothing to get through because the light's first filtered to be in the horizontal state, and then it's going to get blocked because there's nothing in the vertical state. And that's exactly what happens. So the horizontal filter prepares that light in that horizontal state, but the vertical filter completely blocks it. But things can get really weird when we insert a third filter. And this really kind of shows how how superposition can exist in the natural world. So if we insert a third filter in between the horizontal and vertical filter at a 45-degree angle between those two, suddenly you'll notice some of that light will make it through all three. So before you have the two perpendicular to each other, you'll notice that no light will get through. It'll just be black. But if you pass a 45-degree filter in between it, if you just put a third filter in between it and angle it a little bit, you'll see light actually come through the vertical filter. So how does that work? The only job of those filters is to block light. How is three filters allowing light through, whereas the two filters doesn't? And that is exactly what's happening in a quantum computer, where this is the polarization behaves like a quantum state. These states can exist not just in one orientation, but in a superposition of orientations. So when the light passes through the first filter on the right side, that's a definite state. It's purely horizontal. But the diagonal filter, it doesn't block or pass the light simply. It re-prepares the photon into a new state. So it's halfway between horizontal and vertical now. It went from a horizontal state to now a new state between horizontal and vertical, which is superposition. And so after the diagonal filter, the photon is no longer just in the horizontal state. It's back to a mixture of the horizontal and vertical states. And so that means the final vertical filter can now transmit only a part of that light, the vertical part of that superposition, through that third filter. And so it's powerful. This example is pretty powerful because it visually demonstrates that key idea in quantum mechanics, that measuring or filtering a system doesn't reveal what the system already was. It can actually change the state and create new superpositions. And you can see this with just your polarized light. So you'll have 25% get through the diagonal filter, and then 12.5% of the light gets through that vertical filter at the end. And that's why you see the light get dimmer and dimmer. But light still passes through because that diagonal filter turns those photons into a superposition state. So you can actually witness this stuff with things in your own home if you use two pairs of sunglasses and put your phone screen behind it, for example. You can see how superposition can allow a change in state so that the photons can pass through in a way that they weren't able to before. So what does that actually look like when we put it into a quantum computer? And quantum computers look like the computers back in the 1950s. These are actual quantum computers. There's 3 different ones. So IonQ is a large quantum computing provider based in the US. D-Wave is a large provider based in Burnaby. And then Rigetti, I'm not even sure where they're based. I think they're based out of the US. But you can see overall that their quantum computers are very big. There's a person in there for scale. And most of that is shielding and cooling equipment to make sure that those qubits stay in a coherent state, that they stay stable, basically. Because what we don't want is anything interfering with that superposition state and it being measured prematurely and collapsing to 0 or 1 before we want it to. And so most of this equipment is just shielding. But in the slide before, you saw what the actual QPU, the quantum processing unit, actually looks like. So what's the difference in performance-wise in quantum versus classical? I won't spend too much time on this, but really the main thing is that in classical computing, adding more bits increases the computational power linearly. So if you have n bits, you can represent 2 to the n different states, but you can only process 1 state at a time. Whereas in quantum computing, adding more qubits increases the computational power exponentially, mainly because of superposition, entanglement, and a few other features. The system with n qubits can represent and compute across those 2 to the n different states all at once, where the classical case was 2 to the n different states, kind of 1 at a time. But quantum allows for that computation across all those states at once. So because each qubit can be in a position of 0 and 1, and you have them entangled, that number of possible states in the system grows exponentially, which is the main provider of the additional computational power. And so there's a few caveats when it comes to quantum computers. They're not perfect, and I do have a slide a little bit later that talks about where we're currently at with quantum. But while the theoretical computational power of the computers grow with the number of qubits, there are still a lot of practical challenges. So there's error rates. The quantum systems, they're highly susceptible to errors due to decoherence and noise. Decoherence is what I talked about earlier, where you have a qubit in a superposition state and something interferes with it and it snaps to 0 or 1 before you want it to, and it decoheres basically from that quantum superposition state. And so quantum error correction is necessary to be able to overcome that. So you have to, in these noisy quantum computers, you have to have a tool that does some error correction to those qubits to make them stay in a coherent state long enough that we can actually use them. And these are done through quantum gate operations. So the way the quantum computers work, they have to be very precise and they have to maintain that coherence over many different qubits. So you can see how it starts to get pretty complicated. And then it just becomes a scalability problem. So building and maintaining a large number of qubits that stay in that coherent state is pretty challenging. And that's one of the main technical challenges right now with quantum computers. So I'll just diverge from quantum computing as a whole to wrap this up a little bit around a bit of a primer of how this works. But just to note that there are more areas of application for quantum technology for the same type of technology or same quantum phenomena that we just talked about. I only talked about superposition and entanglement. There's a whole lot more that goes on, but those are the main ones that you'll usually hear about and that you need to really kind of get a grasp of how this works. But quantum communication, in addition to quantum computing, is a up and coming area where it's focusing on the secure transmission of information using quantum mechanics and transmitting those quantum states. So this is the things like the quantum internet that you might hear about, or how you can have pretty secure communications by having eavesdrop detection by taking advantage of entanglement and those type of phenomena. So when you hear about quantum internet or quantum communication applications, that's focused in its own area called quantum communication. The third one is quantum sensing and measurements. And so that's using these same quantum systems to measure physical quantities at a potentially unprecedented accuracy. So we're exploiting the same superposition, entanglement, quantum tunneling, the same phenomena that we do with quantum computing, but we're using it to measure something. And this is pretty applicable to areas like navigation, using high precision gyroscopes and accelerometers where GPS isn't available. It's applicable to medical imaging, geophysical surveys for oil and gas, for example, or mineral exploration. There's a lot of tools and up and coming technology that deal specifically with quantum sensing. And so we talked about how quantum computers work. They use qubits. Those qubits take advantage of superposition, entanglement, and a few other quantum phenomena. But there's still another important caveat that not all quantum computers are created equal. There's a million different ways to be able to represent a qubit. And there's a lot of different approaches to be able to have that qubit do computations. And so there's two categories of quantum computers. The first one is an annealing quantum computer, and the most common that you'll hear about is a gate-based quantum computer. And so a quantum annealer, it uses kind of fluctuations in the quantum energy landscape to find a global minimum of a given objective function, which is usually expressed as an energy landscape. And so if that makes sense to anybody, you're probably used to optimization problems where you're trying to find a minimum of a mathematical function, which is optimizing a system if you can represent that system in that function. And so that's exactly what these quantum computers are built for. They perform calculations that find the low energy states for different configurations, depending on the hardware's device. And so it only works if a problem can be configured into an energy minimization problem, which is an optimization problem at the end of the day. And so that's where these annealing quantum computers are pretty much only used for optimization problems. They excel at solving these optimization problems because these problems can be mapped onto the models that represent that energy landscape. And so these are your pretty common use cases, like your vehicle routing optimization, maybe your workforce scheduling optimization, your manufacturing processing optimization is built for annealing quantum computers. They can really take advantage of the way those problems are structured and optimize them. And they're one of the main quantum computers available today that can be actually used. And we'll talk about that a little bit later. And so the other side is gate-based quantum computers. So gate-based quantum computers are the more universal quantum computers. They're more closely related to the classical computers that we use today. So these operate by manipulating qubits using quantum gates, which are similar to your gates in your classical PC. And they perform a series of operations. And it really is analogous to how logic gates perform computations in a classical computer. And so these are theoretically capable of performing any computation that a classical computer can. They just also have additional gates called quantum gates that are able to take advantage of superposition, entanglement, and those other quantum phenomena that make a quantum computer tick, essentially. And so these are well suited for a wide range of algorithms and applications. They're what you'll hear about when it comes to cryptography. These are the quantum computers, these gate-based ones, that are able to crack Shor's algorithm, for example, in the future. These are the ones that will be doing a lot of the quantum simulation, so understanding chemical reactions, understanding the physics of molecules, and simulating those small environments. They're also pretty potentially well suited for all your machine learning applications. Again, basically, they can potentially do whatever a classical computer can do in the future. They just have they're a lot more sensitive to those limitations that we talked about earlier. Gate-based computers are more sensitive to the higher error rates within those qubits. The coherence times are currently pretty short. There's not a lot of qubits available yet to be able to take advantage and map problems onto those quantum computers. And so right now, we're seeing a lot more use in the quantum annealing space, even though it is more specialized for optimization problems, just because that annealing quantum approach is able to get more information out of a problem, given all the noise and error rates, versus a gate-based quantum computer that's limited in the number of qubits that it has available. So just to end this section off around what quantum is, what problems are not for quantum? What are not suited for quantum computing? And there's a lot of them. So your simple basic math and logic operations your classical computer can probably handle that. Highly sequential problems are not well suited for quantum computers right now because each step depends on the previous step, and that requires a level of coherence that we don't see in quantum computers just yet. So if you end up with an error, or you end up with a high rate of errors in one step, that's going to propagate through the entire system and in a sequential problem. Memory intensive tasks, right now, qubits are limited on these quantum computers. They don't have a lot of physical qubits available. And there's even less logical qubits because sometimes you have to use 2 qubits to interact to create 1 qubit, depending on the actual topology of the quantum processing unit. So there's just simply not enough qubits available on quantum computers today to do a lot of the calculations that we think they can do, such as Shor's algorithm, which will essentially crack RSA encryption. Real-time applications, they can be good for quantum computers, but right now, if you need that low latency, low error responses, they may not be the best, but they can be in optimization scenarios. And then interacting with quantum computers that require, maybe a kind of drag and drop type of interface to be able to build your problems. Right now, a lot of work done with quantum computers is at the code level. So you're interacting with them using a classical machine. So you're usually writing Python code that can be understood by an interpreter before that interpreter sends the commands to the quantum computer and then gets it back and is able to interpret it back into language that you can understand and so on. So right now, it's pretty code intensive to be able to work with quantum computers. So overall, quantum's up and coming, but these are some use cases where it's not quite there yet. And so just to expand on the quantum computing landscape while we're on it, to kind of where are we now? What can you actually do with quantum computers, and what does that look like? So the current state of quantum computing, and you'll hear about this quite a bit in the news, we're currently in the noisy intermediate scale quantum era, so the NISQ era with quantum computers. And that's where we have a smaller number of qubits. We have that high noise, those issues I talked about, the limited coherence, so how long a qubit can stay in a state of superposition. And there's not a lot of error correction the error correction isn't quite up to par to be able to handle all of this noise. And so it relies on algorithms that help mitigate and correct those errors. So right now we're in the noisy intermediate scale quantum computer era, but what we want to get to is called the fault tolerant quantum computing era. And this is where we have, as the name states, quantum computers that are similar to our classical computers today, where you don't have your computer randomly flipping bits accidentally in the CPU based off of radiation from the external environment. They're very well built and they're very reliable to the point where we don't even think about it. Your computer just works. And so that's where fault tolerant quantum computers are trying to get to, where they have a high number of qubits similar to the bits in your laptop, potentially millions of physical qubits, whereas right now we're at about 2,000. And they would have extremely low noise, so they would have those low error rates to begin with, and they would therefore have higher coherence time. So you'd be able to have and hold those qubits in a state of superposition for longer. And they wouldn't need error correction or full error correction at that point. So they would be fully error corrected throughout the entire QPU with all the physical and logical qubits. So we're not quite there yet. We're still in that NISQ era, but where can we make use of these noisy machines today? So in the next slide, I'll talk about that, but I added in this neat little chart that somebody made around what does that actually look like and what does that look like going forward. So those error rates we talked about, here's as how you need lower error rates to be able to tackle problems. So you can see the error rates are getting smaller. And then we need to increase the number of qubits as well. So it's not just the number of qubits problem, it's also how do we get these qubits as reliable as possible. And so you can see where we are right now. We're at about 100 to 1,000 qubits, somewhere in there. Some providers have around 2,000, 3,000 qubits, but that's just physical qubits. When you have when you have to actually do computation, sometimes you have to chain some of them together. But overall, you're seeing where Quantinuum, IonQ, Rigetti, IBM, where they live. And to be able to do quantum chemistry, for example, without error correction, we're getting close to that. If we could get better error correction, we'd get close to that area where we wouldn't need error correction if we were to increase the number of qubits. But what really points out here or stands out here is where RSA encryption will be broken. And that's when you start getting into the millions of qubits. And so Shor's algorithm is the algorithm that can potentially crack RSA encryption, where RSA encryption is the protocol and the standard of pretty much all internet traffic on today, and all encrypted devices rely on RSA encryption. So basically, Shor's algorithm can factor the prime numbers very quickly versus a classical computer that would take billions and billions of years to be able to crack even one 2048-bit RSA code. And so you can see that we're not quite there yet. We do need a combination of better error correction, but mainly for that one, we need way more qubits. So we're a little ways away from that yet when it comes to quantum. So where are the use cases that we're seeing it today? So we understand a little bit, hopefully, about how quantum computers work and what makes them different. So how can we actually apply them in industry? Where can we make use of those noisy intermediate scale quantum computers? So the biggest area that we've been applying it is in the optimization space. So using D-Wave's quantum annealing quantum computers, we are able to tackle quite a few different types of optimization problems, mainly around vehicle routing, scheduling, logistics optimization. There's some use cases around portfolio balancing for finance, risk analysis. That kind of fits into the optimization problems. And then we're also seeing a lot of interest in cryptography and cybersecurity. Really, this area doesn't have a lot to do with quantum computing. What we're trying to do when it comes to cybersecurity or quantum safe encryption is harden existing technological assets against quantum attacks in the future. So where you saw RSA being threatened once we get to millions of qubits, how do we prepare for that? And that might seem far off, like we don't really care because that's, potentially 10 to 15 years away. But there's a problem with that where criminals can steal your data today that's encrypted using the standard RSA protocol. They can steal that data today, and all they have to do is just wait. So they can just sit on it for 10 years until quantum computers are widely available that can break RSA encryption, and then they can crack it open. And so for data, healthcare data, for your SIN numbers, for any information, personal information that doesn't change, that's a huge threat right now. So cryptography and cybersecurity focus on how do we implement quantum safe encryption standards. But there is a quantum aspect to cybersecurity and cryptography where you can use what's called quantum key distribution, which is using quantum computers directly to facilitate that to facilitate the security of those systems, using it as its own kind of cybersecurity protocol. Machine learning and AI, we're not seeing a lot of use cases just yet. Financial and modeling and risk analysis, again, seeing quite a bit of use cases on the optimization side, but there's still some models around derivative pricing that they're trying out using gate-based quantum computers. And so we're not quite seeing as much uptake there besides your standard optimization problems. And then quantum chemistry and material science, that's where that area is still pretty well in the research phase where there's not a lot of industry applications, but it is very heavily investigated in an academic sense, where they're doing a lot of this in labs and building those use cases out, which again is further advancing the quantum computers themselves. So if we look at the timelines for these, kind of just iterating what I just said, with optimization problems, we're starting to see those already. So we're starting to be able to put some of that into production, and that'll be available in 0 to 5 years. Cryptography and cybersecurity use cases, that's getting towards 5 to 10 years away, where mainly the big threat is Shor's algorithm. Machine learning and AI, still kind of just in that POC stage, but we're starting to move into the scalable side. Financial and risk model analysis, again, there's still that proof of concept. Whereas the quantum chemistry and material sciences, we just have barely going into the POC stage because most of it's still research-based. So overall, we can see that optimization problems are the furthest along, mainly due to quantum annealing capabilities. And they're getting into the scalable territory where there's quite a few different optimization use cases in production that we've helped out work on as well with clients and across the industries that are actually using quantum annealing in addition to classical optimization approaches. in a scaled environment. So just to touch on kind of how this ties into AI, in short, it doesn't. A lot of people ask if quantum is, how related is quantum to AI? How is AI going to help quantum? And quantum computing, again, is a completely different way of computing. It's not a subcategory of AI. It's not artificial intelligence inherently. But there are some applications where you can pair them together and where they work well together. And so we can combine the strengths of AI with the strengths of quantum computing, and you can kind of use the best of both worlds. So you can use AI to reduce a search space and then use quantum to solve those deep simulations. There's also quantum neural networks that are being developed, or else you can use AI, for example, to select potential molecule candidates and then have the quantum computer simulate that behavior. So you can kind of use AI as a precursor to quantum or after the quantum computer produces its results. So you can use them both together. And there is actually another benefit to the whole AI boom for quantum computing. And that's kind of as we look forward into the next few years. So I talked on the last slide about the use cases and their kind of time ranges before they're really widely available. And what I like to talk about too is that with the proliferation of AI and the barriers that have been kind of knocked down when it comes to being able to access AI tools, that's going to really help speed this up, I think. So back in the day when we had AI emerge, we had AI in cloud start to be able to really push AI models forward. Then we started to see quantum expansion now come into the 2025s through the 2030s. But as people have more access to knowledge around quantum computing, they have access to LLMs, ChatGPT that can help facilitate the actual development. You can vibe code your way through a lot of quantum computing applications. It just really breaks down the barriers even further for people to get involved with quantum computing. Even if they don't have a large computer science background, you can still get involved. The way the providers are approaching this is to make it as applicable to the most people, to make it just another branch of computer science, essentially, where you don't need to be a physicist. You don't need to understand how the quantum computer is working necessarily. Just like most people don't understand how their laptop's working at an electrical engineer's level that they might know. It just works. And then the software that facilitates all the workloads is where people will be able to spend their time. And as AI tools kind of keep getting developed, that's just going to make that even easier to access. So I think I'm running out a little bit of time, but I'll go through really quickly. Where we spend most of our time on CGI Quantum is we don't focus on the research. We spend most of our time finding ways that we can actually implement this for customers. How can we actually implement quantum computing technologies into industry and solve problems? And so we have a large team that can do that. We work with all the large quantum providers. And we also have access, we provide some additional funding or POC tools to be able to help push a POC along, for instance, for a client. We can help fund some of these opportunities to get started with quantum. I won't go too much into our capabilities because it's pretty standard. We identify the problem, then we find the best quantum computer suited to solve that problem, and then we can actually develop and build that solution from a POC into potential production. We use a multi-partner approach to facilitate that. So we can take whatever problem a client or an organization has, and then we can match it with the proper quantum computing architecture that's built to solve that problem. So if it's an optimization problem, we'll probably use D-Wave. If they're exploring some simulation use cases, we'll probably use Quantinuum, Rigetti, IonQ. We have access to all these quantum computers to be able to efficiently solve any problems that come our way. And we've done this in quite a few different areas. We do some consulting as well, just around the state of quantum computing, where we kind of cut through the hype. This is a project we did for a consortium of utility companies in the Netherlands, where they were wondering how they could apply quantum in the future. What does the quantum computing landscape look like, and where can they apply it in their organization? So we identified some barriers, and we then provided some recommendations on how they can get started with POCs and what's real, what's actually possible. And you can actually find this report online, but I think it's currently in Dutch. I don't think it's available in English just yet, but our quantum team in the Netherlands was facilitating that work. We've also worked with some retail clients in Canada, for instance. This is more of an application side of quantum, where we actually developed a quantum optimization platform that used D-Wave's quantum annealers to basically efficiently route delivery trucks. So given a set number of delivery locations, they all start at the depot. We have 6 different trucks. They can carry so many units of cargo. Each location's demanding certain units of cargo. How can we efficiently optimize and minimize the distance traveled by all those trucks? So again, trying to minimize an objective function. It's an optimization problem. How can we optimize the use of those trucks? How can we minimize the distance traveled while maximizing the space on the truck? So kind of sounds like a complicated problem, and it's a perfect use case for applying quantum computing in the real world. So applying quantum annealing overall. And so just to end it off, we do have a few other use cases where there's some concrete results. Port of LA implemented a quantum computing optimization program that resulted in a lot less crane usage, a lot less travel distance for those cranes, wait times were reduced. Workforce scheduling examples where they saw a drastic reduction in scheduling times and planning efforts. There's some use cases that we've worked with around how to place cell phone towers efficiently in a given location, given a lot of constraints around how to minimize the overlap between cell phone signals, for example. And so overall, we have a lot of use cases. I think just for brevity's sake, I can pass these along afterwards if anybody is particularly interested. We also do have some demos where we can show this in action and show actually how to talk to a quantum computer, send questions to it, and get results. But I'll just end it today with how can you actually get involved with quantum computing today? And so this is where it can be passed over to the audience here, where a lot of these technologies are available for pretty much any organization to use. So the best way to get involved is to join the publicly available quantum platforms. So Azure Quantum, AWS Bracket, D-Wave has their own API. You can access Rigetti, IonQ, and Quantinuum through Azure or AWS, or you can go to IonQ's website and you can access their hardware directly. They have a lot of training material available. D-Wave has training material, training courses that you can take. They cost a little bit, whereas AWS and Microsoft Azure have training courses that are available for free, but they're not as in-depth. But overall, you can access these tools today. And so you can take these tools and you can look inside your organizations and identify where these problems might exist. So where optimization or simulation problems exist, where is your optimization algorithms currently hitting their limits? Do you have models that are taking 20 hours to produce a response? Are you running into issues where under certain constraints, your optimization models might not produce a feasible result? This is where you want to identify those types of use cases once you have access to those quantum computers. And then you can partner with someone like us with CGI, where we can help facilitate a lot of the development. We can facilitate a lot of the training, and we can actually help you build out use cases and put them into production. Or you can partner with academic labs. Most universities, I think the University of Manitoba has one, an academic lab focused on quantum computing. And most of these labs are looking for industry use cases. The researchers there are happy to help organizations, and in turn, they get a realistic playground to be able to apply their research. So you can partner with organizations, but you want to spend some time training your teams. So even basic quantum literacy will be a competitive differentiator. We saw that a lot of these timelines are 0 to 5 to 10 years away. But even getting started now by joining these platforms, identifying some problems, doing a little bit of playing around will be a big competitive differentiator going forward. Nobody really wants to get left behind, similar to how we don't want to get left behind with AI. Quantum computing has potential to be quite similar, where it'll all of a sudden just kind of sneak up and be widely available like ChatGPT was. So training your teams is a great investment to make. Even just a small bit of quantum literacy goes a long way. And then if you do want to do some development, you can start small. So we suggest to always start with a small proof of concept where you're just solving really small problems. If you're just doing this alone, trying to better your skills, your organization skills, you can start hackathons with a small problem. And when you do that, starting small with just a small POC, it really does build that capacity for tomorrow. You build those skills, you have a foundation that you can now leverage in the future to be able to build out more complicated use cases. And so overall, that's a great way to go. So with that, I think I can end it and open up for questions. We went through a lot. Hopefully everybody stuck with me through the more rambly parts around how quantum computers work. But that's really the basics of it. And then we talked a little bit about where the use cases are now, what's the differentiators between quantum architectures, and how you can actually apply those in industry. So thanks everyone for giving me your attention, and I can answer some questions.
Okay, thanks very much. Thanks very much, Curtis. I just wanted to make sure that you were good. Like, you can see the questions under the Q&A tab, and if you're fine with going through. Otherwise, I'm happy to read through. I think you've actually answered most of them, but I just want to make sure that you're good with what you see there.
Yeah, no, I can see the Q&A now. So what is the single most practical first step an organization should take today to begin building that quantum readiness? I think pretty well what we just talked about. Actually doing some of the work, actually doing some of the development, understanding how it works. So even just that basic understanding of how quantum computers work, that basic quantum computing literacy, and then just getting access to a quantum computer and going through some of the training available. That's free online. Some of it's free, some of it's paid for, but that's probably the most practical first step for an organization. To build quantum readiness without the development side, that's just as well too. Especially when it comes to cybersecurity, you might want to start looking into what kind of data you're storing, where that data is being stored. Have you ever had a security breach in the past? Does somebody have their hands on that data? Should you be switching to a NIST approved quantum safe encryption method like Kyber or lithium versus RSA in the future? But overall, quantum readiness just comes down to education. So being aware of it and understanding the use cases and understanding where it could potentially fit into your organization in the future, and then keep having those kind of conversations.
So I would think too, like, even the starting point for probably many organizations is even saying the words quantum computing and then asking the question, at the leadership level in particular, of what is it and how might this impact us? Getting curious, right?
Mm-hmm.
As opposed to thinking that it sounds like something that's so far off and people will bring it to us when it's relevant. No, it sounds like it's the recommendation is internalize and get curious about it first.
Yeah, you don't want it to be brought to you too late. I think a lot of the focus on quantum computing now that we're seeing lately, we started our practice quite a few years ago, and there wasn't nearly as much interest in quantum computing. It was kind of that far off, cool, new technology. But since you started to hear more in the news, especially when NVIDIA started fighting with D-Wave and a lot of the other quantum computers saying that it's not real, and then the D-Wave and IonQs of the world started to push back and say it is real, we have use cases, and here's the technology. And then you started to see a bit of an arms race. And then you started to see a lot of people think, ChatGPT had its moment where it came out of nowhere and it kind of upset everything, every organization. And they don't want to be left behind when quantum has its similar type of ChatGPT moment in the future. So that's a big part of it, I think, as well. And so somebody asked, could you please share more details about specific optimization problems that are being solved with quantum computers? Some of them are moving to prod. And yeah, actually, I'll go back to this slide where there are a few use cases. A lot of these types of use cases are very well suited to move into production. The way we assess these before we move into any type of production is we benchmark them against a classical use case or a classical approach. So we will basically run two tracks in parallel. We'll do the development of a quantum approach, and then we'll also develop a classical approach using Gurobi or OR tools or some solver to optimize the same problem, but using classical hardware, usually in Azure or in a high performance compute environment. That way you can see right away that there's potential. You can see if there's benefits to a quantum computing approach versus a classical approach. And those benefits might not be just speed or accuracy. They can come in kind of some strange ways, like power consumption, for example. If you're solving a large problem that's going to run for 30 hours a day, or you have to pay for all this compute time in Azure for, say, 15 hours a run, that can get very expensive. Whereas a quantum computer, say it gives you similar to results to a classical computer, the power consumption for it is exponentially lower. So you can save money by getting a similar result with a quantum computer for lots of use cases by just lower power consumption to be able to get there. So that's a big way to be able to justify the benefits to be able to move these into production. So where you're seeing a lot of use cases being put into prod are exactly examples like that. So where you're optimizing a large complex model or a large complex system. So in the Port of LA, for example, Port of LA is constrained by land. They can't expand their port anymore. They have to basically make use of the area that they have. And so they have to be able to handle their cargo as efficiently as possible. And so they are able to they implemented a production use case for D waves and annealing, where they used it to optimize all kinds of different scenarios. So everything from how the cranes move to where they store the cargo to how long trucks are waiting out front, how you move those trucks through the lots, and how all that changes together. And so you can see how those problems become vastly overcomplicated, very quickly. And so that's probably the best use case, is where you have a large complicated problem like that. Workforce scheduling is another good one, where you have, say, hundreds of employees. Those employees all want to work at different times. They have to adhere to, say, a max number of hours worked before they get time off. There's bargaining agreements that you have to account for in your constraints. And so you can see how trying to find a weekly staff schedule for a large number of people can be also very complicated. And in this use case, 4 million decision variables with a combined 4 billion interactions between them. So oftentimes these type of problems can be large for any classical approach. Another question around how you can contribute to the quantum landscape. The best way for an organization to contribute to the quantum landscape is to be able to find ways to be able to implement quantum. So most organizations aren't going to have the capacity to take on, say, a quantum research project where you're going to invest a bunch of money to do some sort of simulation. The best way you can do it is try and find a realistic use case that, say, an academic lab can come and help you implement, or someone like CGI can come help implement, and that you'll get a benefit out of it as well, so that you're not just investing money, you're also, you're getting an ROI for that. And by using quantum technology, you're inherently helping push that field further by, providing funds for additional research to some of these companies, depending on whose hardware you use. You're providing instant feedback about how these quantum computers work for certain use cases. Those real world use cases are going to be key to pushing quantum forward. So the next question, what about languages or packages like Qiskit or PennyLane? Would they help in development of quantum computers? Yes, they are a very good way to go. So you can actually work with Qiskit. So IBM Q, that's what I have on there in that first bullet. I'm referring to IBM Qiskit. And so Qiskit is a entire kind of software stack, Python libraries, and it gives you all the tools to get started with quantum. And I think they even give you simulator time for sure. So you can use IBM's quantum simulator, but I think you can actually use their quantum computer as well when you're going through all the problems to solve them. So Qiskit is a good one. It's pretty powerful. It's open source, and so anybody can sign up. I think you can get a certification from it as well if you go through their training tracks. PennyLane is another similar library, similar to Qiskit, except it's built by Xanadu, which is a quantum computing company based in Toronto, actually. And so PennyLane's a real popular software or Python library to be able to interface with quantum computers. And it has a benefit that has a lot of production use case capabilities as well. So what you do in PennyLane to just test things out and build POCs, you can continue to use PennyLane throughout, scaling that solution in production. PennyLane's built for kind of that industrial use of quantum. PennyLane has some advantages where you can use it to interface with pretty much any of these providers that I have on the screen. So you can use it to work with Quantinuum, IonQ, Rigetti. You can even use it to work with NVIDIA's quantum simulating capabilities. If your organization has NVIDIA GPUs available, you can use PennyLane to simulate quantum computers or qubits on that NVIDIA hardware. What are the fundamental requirements for establishing a quantum computing lab at university? Is CGI able to provide support for such an initiative? We definitely can support that type of initiative. I'm not sure what the fundamental requirements would be for a university type of program, based on what research capabilities you would need. But we do work closely with lots of other computing labs and quantum computing labs across other universities. So we work with a lot in Europe. We also work with a physics lab and a computing lab in France. So there's a physics lab and a big computing lab, and CGI that kind of have a three-pronged approach to providing access to PhD programs focused on quantum computing through those two labs and CGI. So we work quite closely with a lot of academic computing labs. We also work with Quantum City out of the University of Calgary. We work with them quite a bit. We sponsored their QConnect conference just recently in November. So we work with a lot of local labs as well. We'll also be at Quantum Days in Victoria if anybody's going to be there as well. And so that's a pretty key part of our approach, is kind of contributing back to academics and research and working with those researchers and PhD students and postdocs to find ways that they can apply their research in industry. And some ways that was, as an example of that, we worked with we've been having discussions with a few researchers at Quantum City and the University of Calgary, where they focus on a lot of quantum sensing research. And so we're working on connecting them with some oil and gas companies that have the infrastructure already in place that could potentially facilitate some of these quantum sensing technologies that are being researched. So that's a pretty big part of it. I'm not sure what the fundamental requirements would be for establishing a quantum computing lab at a university, but we can definitely help connect you to the other labs that we work with. I think that would be a great place to start. Efficiency and speed, but what about energy? If we can save energy, it would make it more viable. Yeah, exactly. So that's what I was talking about a little bit earlier about benefits, kind of those quantum adjacent benefits, where you're maybe not getting a better result or a faster result. You might be getting a similar result as a classical computer, but you might save energy in the process just because it can find those solutions and it can search that solution space so much faster. So do you think for small business owners like builders and construction industry, quantum computing can do something? There probably is. That's a interesting industry. I haven't thought too much about construction, but it definitely could, especially if you do any type of logistics planning. So if you're trying to get your lumber, your materials to a build site from another site, and how do you more efficiently do that? How do you schedule delivery of these materials? Those would be good use cases for quantum in the construction industry. So any of those kind of scheduling optimization ones, even the workforce optimization problems, for example. It's just as long as that problem that you have is complicated enough that you really need that extra horsepower to solve that.
Great questions. I see the note from Shaylin that we have reached our time for all questions of Curtis. So can we just get another round of applause for Curtis, please, and for CGI? Like, having a glimpse into your specialized knowledge has been quite incredible, like such a way to spend the lunch hour learning about it. We do record the session, so Shaylin's going to post it to our YouTube channel in the very near future, so you can go there to hear more about some of the great insights that Curtis has shared here today. And Curtis, are you okay? Like, should anyone have a question about like, hey, I really want to set this up at my post-secondary, they can reach out to CGI? Okay.
Absolutely. Yeah,
Okay.
reach out anytime, either through LinkedIn or my email on the screen. I do really like to speak in university students and university programs around quantum. And specifically what we talk about is what are the actual applications in industry. So we pretty much focus solely on, when you graduate, what are the options to be able to implement this stuff? What are we seeing today? How are companies actually using your research, kind of relating it to, here's what's going to happen, or here's what's currently happening outside of academics. How are we applying quantum? And I think that's pretty powerful to have students who are doing that research be able to connect it to real life use cases that maybe they hadn't thought of, that we've come across. So yeah, very happy to talk to anybody in academia or in industry. Anything quantum, I'm happy to chat about it.
All things quantum, great. Well, thank you again, Curtis. It's been such a pleasure to hear your presentation. Folks, you're going to be returned back to the Remo platform floor, so you'll be kind of plunked back at the tables you were at before the presentation started if you want to hang around until 1:15 when I think the Remo event officially ends. So thanks to everyone for being here. And again, thank you, Curtis and CGI, for shining a light on a little bit of the quantum computing that you have in-house. Thanks so much.
You bet. Thank you.
Okay. Bye, everyone.